Okay, let's start. So, last time, just to recap a little bit. So, things that we covered last time. Um, so, first thing we went over was embedded system characteristics. Um, Anyone remembers what all we identified with embedded systems? Dedicated function. Okay. What else? So, coupled with something physical. What else? What was the third thing? Constraints, right? So real time, and we discussed a whole bunch of other. Uh, so which all came from the fact that they was physically coupled. So we talked about real time, we talked about power, and there were a bunch of others that we kind of discussed. Okay, so that was one part. Um, then we talked about different ways we can uh, do computing. So we kind of introduced the concept of an embedded platform which had a computing core, sensors, actuators, some sort of a power system, some way of communicating with peripherals and other things, and possibly some user interface. So we talked about what an embedded platform look like. We talked about different forms of computation, microprocessors on one extreme, custom chips on another, and there was a whole spectrum, and how for things like speed and power, sort of ASICs offered better power, better performance, application-specific circuits, microprocessor at the other end, and then we talked a bit about cost and how cost kind of differs between whether you are looking for low volume or high volume, because it was the whole fixed cost versus recurring cost thing. So we talked about cost and recurring versus non-recurring. And then we started going into microcontrollers. So microcontrollers, what's a microcontroller? What's the difference between that and microprocessor? Yeah, so it's like memory, program memory, data memory, stuff, and peripherals, which typically tend to be on the board, are now sitting. So kind of the name microcomputers is a whole sort of at least a big part of a computer single sitting on a single chip. Okay, so that's what we had done. Let's move back. We talked about how there's a fair bit of diversity of these devices and kind of a whole bunch of metrics that come into play. The market for this thing is very different in the sense instead of just this one dominant player, namely Intel, there's a whole multiplicity of players. Also, even from a single vendor, as I had shown, there's kind of a whole bunch of configurations of these things available. Very price sensitive, high volume, low price, that kind of a market. So picking that on that, and kind of a typical platform kind of just looks like this. What we are using in this course for the assignments and also as the core for your project is this platform called Hexaware. It's a wearable IoT platform. That's how they kind of call it. But it's basically a smartwatch, the similar kind of sensors, accelerometer, gyroscope, things like that. But it's programmable in a variety of ways. So programmable down to bare metal programming, as they call it, which is kind of you can really you can put your own operating system or have no operating system if you want. Really kind of on the bare hardware that you can program. This system has two microcontrollers actually. There's a main MCU, which is this big chip here, and Bluetooth low energy microcontroller unit, which is sitting over here. And this is kind of a little thing, as you can see, sort of it's a ARM Cortex M0, which is kind of a very low-end microcontroller. It's still 32-bit, and the main MCU is an ARM Cortex M4, 120 megahertz, a fair bit of flash and SRAM that exist. And then there are a whole bunch of other sensors, kind of hard to read out here because of yellow color on this thing, but variety of things kind of sitting out here. Those names may not make sense, but they correspond to different sensors. There is a little USB port and all. Okay, and you can program it using 3 or 4 different ways. The one we are going to do is to use it using the Embed Platform, which is what we're going to do. So this is a breakout of what this platform looks like. So the main thing is that the actual platform is this guy out here. It's shown in a wristband kind of thing, but on board it does not have things necessary to program it. And also the interface which comes out of this device, which going back out here, is this thing, which is actually quite tiny and very hard to work with. So what they do is they also sell breakout board, and kind of that device plugs into it somewhere here, and then there are various places you can access different pins and all. And also on the board they have yet another microcontroller which handles the program and some other circuitry which handles the programming of the main device. So handles all the details of talking with tool chains, putting in the binary code onto the device. So in this diagram, this part is the docking station. So this corresponds to this, and everything else is this device. And you'll see a whole bunch of sensors out here. So which is kind of a nice thing about this platform, because a lot of these things tend to be individually quite expensive, and by the time you connect them at board level, things can be unwieldy and expensive as well. It also has, as you notice, a whole bunch of user interaction kind of goodies as well. The MCU that it uses, and one which you should become intimately familiar with to be able to work with that, is this long name, but it's kind of a family of MCUs, and all these code words stand for what kind of package it has and how many pins it has and stuff like that. Recall again, these families have kind of lots of devices in it with like some different configurations. So NXP NXP is the company, Connectus is the series, and this what this shows is the kind of features it has. So the main core processor, the one in green out here, is something that they just licensed from ARM. So I guess the closest thing to monopoly in this thing is ARM, because they make the designs which everyone adopts, although now there is competition from the Berkeley RISC-V processor, which I mentioned last time. This particular chip actually in turn has lots of cool, processor core, has lots of cool capabilities, including some instructions for signal processing. And also you see this DSP out there, it is a floating point unit. So it's a pretty reasonably powerful processor, but it doesn't have a lot of goodies that you might find in, let's say, laptop, desktop, or even Raspberry Pi type processors. For example, the way it handles memory protection between the operating system and application, those kind of goodies are missing in it. But that's the main core. Rest of this MCU is all the stuff that normally in a computer you might find on external chips. So starting from the bottom left, security and integrity. It has a bunch of things to help on that front, like for example, computing various kind of codes, random number generator, stuff like that. Then it has a bunch of analog interfaces, analog modules. If you're going to interface with the physical world, that's essential. So what it has out here are A to D converters, and then also a D2 and a D2A converter as well. So this is ADC on this side. This is DAC. Whole bunch of timers. So that's the next thing here. Whole bunch of communication interfaces. We're going to dive into some of the way IOs happen generically a little bit later. Then you'll see clock system up here. That's very important. Clocks and time play a very important role in embedded systems. And then finally, memories. So typically these things will have flash memory for data, SRAM for code, and oftentimes some possibly other flash for persistent data also, like a file system kind of thing. SRAM tends to be pretty tiny. One of the things that makes that you may not at first just kind of think so, but static RAM is extremely power hungry, and that acts as a limit on what size memory that you can have out there. And we don't have DRAMs on these things. DRAMs are your DIMMs that you have on your regular computer. Can anyone think of why they don't put DRAMs on these things? Why do we? So I'm making that assertion, I guess. They only use SRAM. Why not DRAMs?
Some chips are 16-bit or 8-bit, but 32-bit or 2 gigabyte or 4 gigabyte.
Well, you can put smaller ones, right?
Because it's too large.
No. So the main reason is that DRAMs are actually, huh? Say it again?
If it's not recharged in time, the value is decaying.
True, DRAMs do have. Okay, so the main thing really is I didn't expect anyone of you to know it. So let me. The DRAMs are usually made using semiconductor processes, which are very, very different. So having the same semiconductor process both do DRAMs and essentially logic tends to be hard. There are some exceptions, but generally that's the case. So you'll usually not find DRAMs on the same chip as rest of logic. So it's usually just SRAM. So that's why. So the SRAM out here is here, and I guess DRAMs. Because of special processes.
But are there separate modules that can actually be attached to these to interface with the microcontroller units? Like, are there?
Okay, good point. So you conceivably could. One thing you'll realize is very few of these microcontrollers bring out an address data bus for you to connect memory. Okay. In fact, most of the pins that they would have would be dedicated for interacting with the physical world. I think there's a statement which is like almost true 100% of the time. There might be some offbeat chip out there which does have some external memory interface. So memory data interfaces. Now, having said that, you can always use other pins to kind of interact with the DRAM if you want.
Master-slave configuration.
You could, and then you'll have to put a lot of onboard on your printed circuit board, some additional hardware to control the DRAM precisely because what you were saying that it needs to be refreshed and all. So it's pretty tricky. So you'll usually not find it. I mean, you have to be quite desperate to have a DRAM for some reason to go to those lengths. So SRAM is there, but SRAM being very power hungry and SRAM also being very area consuming. DRAM takes one transistor per bit. SRAM is 4 to 6 transistors per bit. SRAMs also leak a lot of power. So all those things conspire together that you usually find things which are well, what does this thing have? 256 kilobyte. It's kind of a fairly high end. Maybe you'll find 1 megabyte. That's it. Whereas DRAMs we now are used to whatever. This laptop has 16 gigabytes, right? So orders of magnitude different. And then you have kind of variety of things for the system support. So for example, this chip does have a DMA, which we talked about last time. That is kind of like a little processor which can move things from peripherals to memory or one area of memory to another area of memory. It also has a memory protection unit so that you can protect different regions of the memory from being written, or you can restrict whether they are read or written. As MCUs go, this is reasonably high end. Okay, not very high end, but it's reasonably high end in its capabilities and all. It's doing a lot in a device like that. Not very far off from what you might find in Fitbits and these kind of things. It's in the same realm of. So in that family of devices that NXP makes, this particular MK64/63 family, the particular one that this thing has is out here. So 1 megabyte flash, 256 kilobyte of RAM, and it has 83 IOs. Okay, so that's what we are using, and there are a whole bunch of kind of details out there which are kind of just verbalizing what doesn't really matter. Main thing that I want you to do is not an assignment, but essentially you need to do it, which is read the fine manuals. Okay, so there's a data sheet and there is a reference manual. Data sheet is a good start. I think my the scale because of the way the screen is scaling is not going out right. Don't have it. Anyway, the I'll post the links on Piazza, but if you just follow one of the slides, you'll find it on the manufacturer's website. That not every feature of this chip we are going to use, but you should certainly make yourself familiar with timer side of things, the various peripherals, sensors in particular, because what you would see is that the libraries that are out there in the Embed OS don't necessarily fully exploit these capabilities. Like for example, a timer may be offered as a generic service, but maybe its accuracy is not sufficient. Maybe you want to do something else. So this getting a good feel of the processor is very important. It's not something you would do, let's say when you're programming on your laptop. Maybe at best you will try to understand the instruction set architecture, assembly language, but for MCUs, it's always a good idea to dive one level deeper. So go through it. Reference manual is much bigger. I think it's like 700-800 pages. So obviously I don't expect you to read that, but when you need to dive into something in more detail, then that's the place to go. Okay, so generally speaking, for programming of this nature, it's good to be very intimately familiar with the hardware. Don't approach it the way you might kind of programming on laptops and desktops. Okay, so I want to spend time on a couple of topics which play an unusually important role when it comes to working with these devices, and in the process go into some of the underlying concepts. So first thing I want to cover in this lecture is energy and power considerations. As you might imagine, particularly for a device, a wearable device and all, that's quite important, but in many other contexts also, it ends up playing quite an important role, things which are embedded and some things. So not all embedded devices are power constrained. They may be plugged in, but a lot of them are energy and power constrained. I also kind of implied out here that plugged in versus not plugged in. So that certainly is one reason why you might worry about energy and power, namely you want to have a longer battery life. Can you think of some other reason why you might worry about how much power is being consumed? So besides battery life.
Mobility, like if you want to.
Well, that sort of comes with battery, right? Huh? Yeah, heat. Heat, yeah, said heat, exactly. That's extremely important. In fact, for devices like our cell phones and all, that is a huge bottleneck because as things heat up, so certainly battery life is one consideration, reasons, and the other is heat. Now, heat has many implications. Firstly, it can get uncomfortable. I mean, that's for sure. The second thing is that when things heat up, they have bad consequences. Things slow down, error rate goes up, longevity goes down, the chip might die earlier, all kind of bad things begin to happen. And third thing is that heat has to go someplace. If it doesn't go any place, what happens? Circuits burn down, that's one thing. What else? The whole thing will start, right? I mean, imagine a pacemaker or a brain implant, right? I mean, if that heat has to go someplace, right? So you have to have thermal balance at some point, right? Whatever you're producing has to be dissipated out into the rest of the universe somehow. Heat has a variety of causes, things. So it accelerates aging, is uncomfortable, and can cause damage to device and can cause damage to environment. So all sort of valid reasons why we would worry about that. Okay, so let's. So when it comes to managing how much power a computer system is consuming, computer system is consuming in the course of doing its job, there are a variety of ways you can kind of approach this thing, and a variety of ways it is approached. So one very common thing you'll find is that processors, and in particular, but also other peripherals, oftentimes have multiple modes, and those modes correspond to some sort of a different balance between functionality and power. So a lower power mode with lower functionality, a higher power mode with higher functionality. So you'll often find things like idle, stop the clock, power, don't supply the voltage, and things like that. And this is equally valid for all other things. It can happen to the CPU, to the memory, to the peripheral. All of them are candidates for this, and of course the whole chip and the whole board. It started out just from CPU perspective, but nowadays memory and all are all handled in the same manner. Some of the questions that when you think about these states, how deep is the state, as in what all functionality is being turned off, and also very crucially, is the state preserved or not? By state I mean when we come back, is the system starting from where it left off, or did it forget something, like did the content of the memory get erased? Okay, so those kind of questions. You save power by changing the modes. That sort of is obvious. When you can get away with reduced functionality, you would change it. The bigger question is how to do it, right? Because the problem is you're trying to do it online, and you're sort of kind of in this game you have to predict. The challenge is that getting into, if you go to sleep, then waking up is going to take time. And so if you make a wrong guess, then the user performance is going to take a hit. If you might recall that until a few years ago, our laptops and all, when you would wake them up, it would take some perceptible time to get up. Nowadays, things are kind of almost instantaneous start, so things have improved quite a bit. This whole approach is called dynamic power management. But that's only one approach. So if you think about it, this is basically saying shut things off when they are not needed. And so philosophically, that's certainly one approach. But there are other things one could also do. So one approach, which is actually not as much of a win as you might imagine, is called frequency scaling. And what this, roughly speaking, relies on is that the power consumed by electronic circuits is proportional to frequency. Okay, so that is what it is relying on. So power is proportional to F. What about execution time? Execution time is also related to F, inversely so, right? You lower the frequency, execution time goes up. So if I change the frequency, the power changes proportionately, and the time, execution time, T execution, is proportional to F inverse. How much? What is energy? Energy is power times time, so that remains constant in this case, right? So from an energy perspective, this thing, so energy is equal to P times T execution, and that remains constant. So, so that's not help. So certainly what's doing is stretching out the computation, and therefore it's certainly going to help us on the heat front, but it's unlikely to help us on the battery life front, right? So just something to keep in mind. Now, power is not just proportional to F, power is also proportional to something related to some other things. Besides, very importantly, power is proportional to square of voltage also in digital circuits, roughly speaking. And what about voltage and frequency? What do you think would be the relationship between them? If I increase the voltage, what happens to the speed of the circuit? Assuming you don't increase the voltage so much that it burns down or damage.
Power increases.
No, to the speed of the circuit. So power obviously increases because it's a V squared term effect. It increases quadratically. Yeah.
It may take more time to charge up or discharge, so it may take longer.
No. So remember, yeah,
Or does it just become faster?
it becomes faster, right? Intuitively, you put more voltage, light bulb shines more, right? Because there's more electromotive force being applied, basically, right? I mean, you think at the physics level of it. So voltage is kind of some sort of an inverse relationship with frequency. Some sort of a positive relationship with frequency. So I increase the voltage, frequency goes up. Okay, it's a more complicated nonlinear relationship, but and kind of saturated at some point, but there's a big region of operation. You increase the voltage, frequency goes up. So this thing is kind of an interesting thing then. Now, how many of you have done digital logic course out here at M16? Nobody. Very few. Okay. So when the speed, every circuit for a given voltage is going to have a maximum frequency you can operate it at before it begins to fail. By begin to fail means that it no longer does its job correctly. So errors start to happen. So for a given voltage, there exists a F max. Or conversely, given a frequency, then given the maximum frequency you want to run the circuit at, maximum speed you want to run the circuit at, you must have a minimum voltage. So, or equivalently, given F, there exists a V min. Okay. Now, what this says is the following. So, going back out here, let's say I reduce the frequency. So clearly my circuit was operating at that frequency. If I reduce the frequency, that means I can get away with a lower voltage now, right? And looking at this, if I reduce the frequency and I reduce the voltage, I have a bigger gain, right? In fact, if you assume, for the sake of argument, that frequency and voltage are exactly proportional, then what this is saying is that power has some sort of a cubic relationship with voltage or frequency, right? I mean, so that's my norm. But what it also says is, therefore, it's smarter to control voltage and frequency together, because just controlling the frequency kind of kept the energy constant. But working with this, if I also say, let's say for the sake of argument, F is proportional to V, then execution time is inverse of frequency. So execution time is V inverse, and so energy would be execution times time power, which would be FV squared times 1 over F, that will be V squared. So energy is V squared. So as I lower the voltage, energy will go down as well. So the strategy which changes both is going to be better, and that leads to the final strategy, voltage and frequency scaling. What intuitively this is saying is the following, that if you have a needlessly fast system, then you're going to pay with a higher overhead all the time for it. It's kind of like you have a, I don't know, Lamborghini, okay, and you're driving it in the city at 30 mph. You're burning a lot of insanely fuel inefficient because it's designed for a different peak operation. So anytime you over provision or have a needlessly fast system, then you pay for it. And one of the ways you can kind of counter that is to lower the voltage. Instead of keeping the voltage unusually high for your needs, you kind of lower it down. So voltage and frequency scaling together, this approach is called dynamic voltage and frequency scaling. Now, of course, the challenge in frequency and voltage and frequency scaling is that you've got to be able to change the two, right? Here you should change the frequency. That's usually easily done. In the MCU, we saw there was a clock system corner, and usually there are circuits on MCUs which allow you to write to some register and change the frequency that the processor is seeing. Okay, so they basically put some clock divider or some other circuit to kind of take care of it. Voltage is trickier. Changing voltage on the fly is usually not something you will find on most MCUs. There are some. Usually it is something done at the board level. Okay, so you might see it at the system level. So that's what I've written out here. It requires voltage regulators where you can change voltage on the fly, but typically it's a system or board level function. Yeah, go ahead.
Can you just explain how to change the frequency a little bit? I was kind of got lost.
How to change the frequency?
Yeah.
Okay. So let's do the following. I'm trying to see how can I add a page to this thing. I knew there was a way to do it. Okay, I'm just going to draw it out here. Okay. So let's say I have some clock signal like this. Okay, with certain frequency. And for now, let's just focus on I only want to divide. Okay, so now I can easily divide by 2 by basically creating, my goal would be to generate a signal which looks like this. That is, every alternate edge of the clock, this thing flips. Now, if and when, I don't know, have you done M16? Digital logic? Never? Oh, okay. There's a special circuit called flip-flop. Heard of it? Yeah. Okay. So what a flip-flop does is the following. It has 2 signals. It has a clock signal and it has a data input. And at every clock edge, it takes whatever is on D and then puts it onto the output. Now, using such a circuit, it's very easy to create arbitrary type of functionality which has memory, in particular this one. So the way you would do this thing is that what you want to create is the following, that I want to toggle, I want to change the state of the output every time the input has some particular value. Okay, I'll let you figure it out how to do it, give some thought to it, but basically by using an XOR gate out there and feeding back, you would be able to create something. It's called T flip-flop actually. So the whole thing is called toggle flip-flop. So you can do a divide by 2 with that. In general, you can do divide by power of 2 very easily. Challenge comes when you want to divide by arbitrary ratios. And heck, what if you want to multiply? Okay. So there's a particular type of circuit called phased. So this is just flip-flop. Okay. But there's also something called PLL, phase lock loop. And they allow for they allow for arbitrary frequency to be generated. And let me give you an intuition for it, while the actual topic unfortunately is way too advanced, but let me actually I can add page here, huh? Okay, so the goal out here is the following, that I have some frequency coming in and I want to multiply or divide it by some factor. Okay, so what we do is we rewrite on like the following. So this is some frequency coming in, and I want the output here to be some number times that frequency. Okay, some ratio. Now, what we rely here on the fact is that there are certain types of operations I can do relatively easily, and in particular, so let's say I want to multiply, but I know how to do division very well. Okay, so let's say I know how to do divide by n for a moment. So what I'll do is, I'll take this guy and I do divide by n. And I showed you how to do divide by 2, and from that you know how to do divide by powers of 2. Okay. So I do divide by n. And I feed back out here, and this is a comparator. What this guy does is it compares the phase. What I mean by that is that it compares how well the two clocks are aligned with each other. And if they're misaligned, it generates an error voltage. And then what I do is, here I have a special circuitry which is called voltage controlled oscillator. It's a clock whose frequency is a function of voltage. So the idea is that as the error goes up, changes, I'm going to feed this control signal to this oscillator. So if the frequency is less, the oscillator will be sped up. If the frequency is low, like a control system, the way you kind of speed up and down. So I'm using this error to control this oscillator so that I'll get the right ratio. Now I showed divide by n, so I certainly have showed you how to do powers of 2. With a little bit more magic, you can divide by arbitrary numbers as well by counting the edges. It's something called, I mean, you have to design something called a finite state machine. Again, you have to wait for a digital logic class to do it, but that's how we do it. So so if you look inside the clock systems of MCUs, you'll find PLLs there, and they will let you program a number by which you want to multiply or divide the clock. Okay, and then up from software level, it's just as if you're writing to a register. Okay. So back to our modes. These things. So like I said, this you can pretty much always do because most of these things will provide some sort of clocking system. These modes, most MCUs have it. At the very least, they will have it full on and everything off. But usually there's a lot more subtlety. This particular processor that we have on Hexaware actually has a long list of modes. Okay, and one of the things I would like you to do in the datasheet is go and hunt for the place where it is strike power and look at what kind of modes they have. Okay, they have a reduced frequency mode, full on mode, and within that they have a whole bunch of categories where different parts of the chip are on or off, and whether the memory retains the thing or not. Like for example, you're going to sleep. Do you want the memory to remember the data or not? Like maybe not. Maybe it's just every time an interrupt, every time a signal from the outside comes, you run the program, process the data, and then you don't really care. It's as if every time you are waking up afresh, in which case you can go to a deeper sleep than otherwise. There are a whole bunch of other peripherals, maybe their state you don't care about. Maybe you want the sensors to be shut down. All those kind of things. So there are a whole bunch of them. But at a very broad level, you can think of them as run, wait, and stop. And all of these things, in case of this processor and pretty much processors, are done by something called wait for interrupt instruction, WFI, wait for interrupt.
Are there possibilities that there can be transient states in which they can be stuck in?
What do you mean by that?
If we have like a sleep and then ready to stay, like if some malfunction happens, get stuck in between.
Oh, like some malfunction and you're stuck in the sleep state or something like that? Usually malfunction is a software issue in this thing, and it happens the other way around, which is actually something that happened a lot on early Android versions, which is you could say don't put to sleep, except you forget to remove the don't put to sleep, and then the battery keeps burning. Okay, so those happen. Hardware, I mean, look, do hardware errors happen? Yes, but the cost is so much that people do a lot of time making sure that it's not buggy. But hardware bugs happen. I mean, earlier this year there was this whole thing about Intel processors and AMD processors all having security bugs, so they do happen. But generally not for this kind of stuff. Okay, interrupts. So does anyone not know what interrupt is in computers? So, okay, some signal coming from outside which causes some sort of exception. What happens typically in processors with this thing is that you go to sleep and then you are saying to the processor, when an interrupt comes, then wake me up again. Okay? That's basically all it's doing. This particular system also has something called very low power something. I don't know what R is. Very low. Yeah, maybe R is for power. Very low power mode, but it's basically a reduced frequency mode. Okay, where kind of it's as if you're working with kind of a slower processor. Anyway, so that's one part. The other thing which matters, and we'll sort of talk about it later in the course a bit more, is that when you move from one state to another, it takes time because you have to restart things or you have to save state. So all of state transition take time. And actually, in the data sheet, they have a table where they show you those things, and those times are in tens to hundreds of microseconds. So they're significant. I mean, if you think about this processor is running at whatever 120 megahertz, so even 10 microsecond is 1,000 instructions. Okay, so fair bit. So there's cost to it. It goes back to the point I was making. There's cost to mispredicting. If you wrongly went to sleep thinking the world is not going to need me, and then pronto the interrupt comes, then you're waking up, and all of that is going to be overhead. So prediction matters, and later in the course when I talk about the strategies for doing this power management, we'll sort of look at those. But for now, you can think of your system as it can move between these states. You can go to a sleep state under some sort of program control using this WFI instruction, and you can come out of it when the interrupt comes. Okay, that interrupt can come from outside. It could also come from a timer. You could arrange for your system to wake up every 1 second, for example.
Generally, I mean, do they add like time buffers so that it takes some, like even in a system, the system takes some time to respond after switching from sleep to wake up? Like, do they like add time buffers on purpose, or
What do you mean by time buffers?
like, I mean, give some time for the system to like come back to normal and like to
Yeah, the hardware will not even start. So when you after the WFI, it like from the point the signal comes from the outside world to the point you'll be able to execute an instruction, there's going to be some time, and that's when the hardware circuits are waking up. And there are essentially two main reasons it takes time. If you put the clock to sleep, that's the oscillator, it takes time for the oscillator to come back at its proper frequency. And likewise, voltages, if you shut down the voltages, it takes time for the voltage to come back up because the capacitors and the circuitry need to charge up, and all of that takes time. So waking up takes time, and therefore cost of incorrectly going to sleep is reduced performance. Okay? On the other hand, keeping up is more power consumption. So you have to balance the two, and people apply all sort of techniques. In fact, to this day, like even now, search for better and better ways. So like the latest is they apply machine learning methods and AI methods and all, because a lot of these things are basically making a prediction about what's happening in the outside world, or how does this particular human behave. So if you can predict better what the workload is, what's happening, when the next WFI will come, then you can make a better, when the interrupt will come, then you can make a better decision about it. So it's really a decision-making process. Okay, so we'll talk about the mechanisms later. But what I just wanted to show is that the gains are quite sort of significant out here. So give me a moment. I think I'm going to change so that you can see these plots better. Yeah.